In Chapter 5, we're going to talk about form tolerances. Okay, so the objectives for the chapter, I want you to follow along with this presentation. Draw the symbols for form tolerances, complete a feature control frame to specify a form tolerance, and properly apply the material conditions. Number 3, explain the extent of form control establishes by limits of size. 4, apply straightness tolerances to control surface elements, or a derived median line to show the interpretation of those tolerances. 5, explain and calculate virtual condition for a regular feature of size that has a form tolerance applied to it. 6, apply flatness to control a surface and show the interpretation of the flatness tolerance zone. Number 7, apply a flatness tolerance for a median plane and show an interpretation of the flatness tolerance zone. And then next, apply circularity tolerances, and then also apply a cylindricity tolerance. Okay, form tolerances. Now, according to Rule 1, a feature must have perfect form at the limits of its size. So whatever the maximum material condition is, the part or feature has to have perfect form at that size. Therefore, a feature's size tolerance controls form up to the MMC limits. Okay, form tolerances are specified only when form variations must be less than permitted by the size of the tolerance. Okay, so if you wanted to control a feature of size to a really perfect form, you put a really small tolerance on it. But if you can give more tolerance, you use a feature control frame for form tolerance to allow that size variation. So therefore, a form tolerance is needed when other tolerances, size, profile, orientation, or runout, do not provide enough controls to control the feature. So here are our basic form tolerances. There are only 4 form tolerances. As you can see, when we talk about this, we'll see that one is an extension of the other. But our form tolerances are straightness. We're going to talk a lot about straightness because it's how we set up our understanding of form tolerances. Then flatness, which I see flatness as being an extension of straightness. And we'll talk about that in a little bit. Then circularity, and then cylindricity. Now I see cylindricity as a extension of circularity, but we'll talk about that in a little bit. So, feature control frame. A form tolerance has only 2 compartments in the feature control frame. It's going to have the tolerance symbol, and it's going to have the tolerance value. So depending on the tolerance, there may be a diameter symbol, or there may not be in the tolerance value compartment. Remember, RFS is always assumed. That's per Rule 2 of GDT. RFS is always assumed. However, an MMC or LMC symbol may be placed in the tolerance value compartment if it is applicable. Okay, so for form tolerances, datum feature reference is never used on a form tolerance. I think that's why we talk about form tolerances first, because the feature control frames are much more simpler than some of the other tolerances we're going to discuss. Okay, here's some examples. This is a straightness. This one happens to have a diameter symbol, and then we have a tolerance. In accordance with rule number 2, RFS is assumed. And then there's no datum feature references. Okay. Here we got another straightness tolerance. We have an RFS is always assumed. Applies in the free state. We'll talk about that in a little bit. And then this one has an MMC modifier. As you can see, the form tolerances are pretty straightforward. Okay, condition modifiers. Remember, in compliance with Rule 2, RFS is always assumed. MMC symbol must be shown when it's applicable. Only used when form tolerance is applied to a regular feature size. Do not show a form tolerance applied to a surface element. Surface elements MMC doesn't apply when a form tolerance is applied to a surface element. When an MMC is functionally correct, omission of the MMC symbol could increase cost. Again, RFS is always assumed unless an MMC modifier is present. Okay, RFS is a little bit more stringent, so MMC modifiers, if they're applicable, should be specified because part costs can go up. Okay, form tolerances applied to single features. Each form tolerance shown below affects the single feature to which it applies. Okay, so what I have here is a flatness tolerance of 4 thousandths, and it's applied to this upper surface. Okay, so it only applies to this upper surface. It doesn't apply to the width, doesn't apply to any other surfaces. It only applies to that upper surface. And we could show it like this, or we could show it on an extension line here, and then we have the flatness within 4. Okay, so this means the same thing. We're talking about the flatness only applies to this upper surface of the part. Okay, form tolerance applied to surfaces and features of size. Okay, so when you're looking at a part, you need to understand what's a feature of size and what is a surface. So this rectangular part, it's a rectangular prism, has 6 flat surfaces. It has 2 cylindrical surfaces, and those are the holes that are features of size. And it has 3 features of size defined by the width, the thickness, and the length. That's what these number designations are. This is L is for location. This is the location of the 2 holes. This S is a feature of size. It's a width. This S here is also a feature of size. It's a length. And this S here is a feature of size. It's the thickness. Okay, so we have 6 flat surfaces. We have 2 cylindrical surfaces. We have 3 features of size. And we have some location tolerances here. It's important to understand this concept. Okay, form requirements. Form limits to size. Perfect form boundary. Size limit controls form per rule number 1. Maximum material condition, which would be the smallest hole or the largest shaft. And then least material condition, that could be the smallest shaft or the largest hole. Now, rule number 1 is the envelope principle. Perfect form boundary at MMC. That's rule number 1. So as the size departs from MMC, your form can vary more. And perfect form is not required at least material condition. Perfect form is only required at maximum material condition. That's rule number 1. And it does not control relationships between features of size. And then this is illustrated here. Okay, so we have a feature here. It's 1 inch. This is a feature of size. And its tolerance says 1 inch plus or minus 10 thousandths. Now, what does this mean? Okay, that means if my part is made at 1.010 at the maximum material condition, that part has to be perfect. It cannot allow any variation. So what we're showing here is the perfect form boundaries. Okay, so if that part is at that size, the maximum material size, it needs to be perfect to fit within the boundaries. So variations may be equal to the size tolerance, but if you had any variations outside the size tolerance, then the part is no good. Okay, so this is another way of looking at it in 3 dimensions. These are our perfect form boundaries, these imaginary planes here, right at the maximum material condition. The part needs to fit within that. So if the part has to be 1.010, then it has to be perfect. I'm going to pick up at slide 15 on the next lesson.